Hello all. Today, let's explore the difference between independent and mutually exclusive events. People who are new to probability theory often get confused between these two events, that is, independent and mutually exclusive events. This confusion is common because these concepts seem similar, but are actually very different. Let's start by exploring mutually exclusive events. Given a probability space, two events A and B are mutually exclusive if probability of A intersection B is equals to 0. That is, the joint probability of A and B is 0, which means that the probability that A and B event can happen at the same time is equals to 0. For instance, when a coin is tossed, then the result will be either head or tail. But we cannot get both the results at the same time. Such events are called mutually exclusive events since they do not happen simultaneously. So, mutually exclusive events are those events that do not occur at the same time. If A and B are mutually exclusive events, then there is no way that these two events can occur at the same time. Mutually exclusive events in probability theory correspond to disjoint sets in set theory, because both concepts describe situations where two events or sets have no outcomes or elements in common. So, mutually exclusive events in probability theory mean the exact same thing as disjoint sets in set theory. If A and B are disjoint, then A intersection B is equals to empty, is a null set in terms of probability theory. So if you probability both sides, you'll get probability of A intersection B is equals to probability of a null set, and we know that it is equals to 0. Okay, so let's see what are independent events. Given a probability space, two events A and B are independent if probability of A given B is equals to probability of A, or probability of B given A is equals to probability of B. Okay, let's try to understand this. Probability of B given A is equals to probability of B. What does it mean? It means that the occurrence of event A does not give any information about event B. So here, when we have independent events, both the events A and B can occur at the same time. But the occurrence of event A would not give us any information about event B. So the outcome of one event does not impact the outcome of other event. Okay, let's try to use the formula of conditional probability and see what do we get here. So probability of A given B is equals to probability of A. If we use the formula of conditional probability, we'll get that probability of A given B is equals to the joint probability of A and B divided by the probability of B. If we multiply probability of B both sides, we'll get that probability of A intersection B is equals to probability of A times probability of B. So what do we get? We got that the joint probability of A and B is equals to the multiplication of the individual probability of event A and event B. Similarly, if we try to use the formula, conditional probability formula, and write probability of B given A is equals to probability of A intersection B divided by probability of A, and then multiply probability of A both sides, we'll get that the probability of A intersection B is equals to probability of A times probability of B. So we can say that two events A and B are independent if the joint probability of A and B is equals to the multiplication of the individual probability of event A and event B. Okay, so two events are independent, two events A and B are independent if probability of A intersection B is equals to probability of A times probability of B. Independent events are events that do not provide information about the occurrence of the other event. If A and B are two independent events, then the occurrence of event B does not change the probability of A. For example, flipping a coin and getting heads. Then flipping it again, getting tails, are two independent events. Let's try to analyze mutually exclusive and independent events. Let A and B be two events, then probability of A union B in general is equals to probability of A plus probability of B minus probability of A intersection B. Now, if A and B are mutually exclusive, it means that the joint probability of A and B is equals to 0. So we get that probability of A union B would be equals to probability of A plus probability of B. But if A and B are independent events, then joint probability of A and B is equals to probability of A times probability of B. So in that case, we have that probability of A union B is equals to probability of A plus probability of B minus probability of A times probability of B. So basically, if we have mutually exclusive events, it means that two events cannot occur at the same time. But if we have two independent events, it means that they can occur at the same time, but the outcome of one event would never impact the outcome of other event. Now, two events can either be disjoint or independent. Two events can never be disjoint and independent at the same time. It would be either disjoint or independent. Okay, let's consider A and B be two events with probability of A not equals to 0 and probability of B not equals to 0. And let's say A and B are disjoint. If A and B are disjoint, that is mutually exclusive. Again, mutually exclusive in probability theory means the exact same thing as disjoint set in set theory. It's just the terminology. Okay, so if A and B are mutually exclusive, then probability of A intersection B is equals to 0. And if we assume that probability of A is not equals to 0 and probability of B is not equals to 0, it would imply that the multiplication of probability of A and probability of B is also not equals to 0. And what do we get in that case? We get that probability of A intersection B, which is 0 because we are assuming A and B to be mutually exclusive event, is not equals to probability of A times probability of B, which means that A and B are not independent. So mutually exclusive events cannot be independent unless the probability of one of the events is defined to be 0. Like if I state that, okay, A and B are two mutually exclusive events and probability of A is equals to 0 and probability of B is not equals to 0, in that case, mutually exclusive event can be independent. But if we have non-zero positive probability of any two events, then in that case, mutually exclusive events can never be independent events. Okay, let's try to look at it with an example. So let's say you roll two dice and let's define event A as that the second die is a 1. B is defined as the event that both dice are displaying the same number. And C is defined as the event that the sum of the dice is more than 7. Okay, so the universal set would contain all the elements, all the possible outcomes when you roll two dice. So basically it contains I comma j such that I could be 1, 2, 3, 4, 5, 6, because when you roll dice the first time you can get either 1 or 2 or 3 or 4 or 5 or 6. And again, j can take any value out of 1, 2, 3, 4, 5, 6, because again, when you roll the second dice, you can get either 1 or 2 or 3 or 4 or 5 or 6. So the universal set contains all the possible outcomes when you roll two dice. So it basically contains 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Roll a die first time, and the second could be 1, 2, 3, 4, 5 or 6, anything. Again, You roll a dice, you got 2, and when you roll second die, you can get 1, 2, 3, 4, 5, 6, anything. Again, so you keep on doing it. So omega, basically, the universal set basically contains all the possible outcomes. And the cardinality of omega would be 6 square, that is equals to 36. Okay, let's look at event A. Event A is that the second die is a 1. So you go back to the universal set and you see, okay, what are the outcomes in which the second die is a 1? So if you see 1, 1, here, the second die, you don't care about what you get in the first die. The first time you roll a die, you only care about the value of the second die, that the second die should be 1. So 1, 1 is a possible outcome. 2, 1, 3, 1, 4, 1, 5, 1, 6, 1. So A basically contains 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1. Okay, and the cardinality of A would be equals to number of elements in the event in the set A, which is equals to 6. So probability of A using the classical approach formula, using the classical formula of probability, that is that probability of any event is equals to the cardinality of that event divided by the cardinality of the universal set. So we get that it is equals to 6 divided by 36, which is equals to 1 divided by 6. Let's look at event B. So event B is the event that both dice are displaying the same number, which means that B would contain elements like 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So the numbers in both the dice should be same. And these are the only possible outcomes that we can have. Okay, again, now the probability of B, again using the classical formula, we'll get that probability of B is equals to the cardinality of B divided by cardinality of the universal set. Cardinality of B is the number of elements in the event B, which is equals to 6, total number of outcomes in the event B, divided by the cardinality of the universal set, which is the total number of outcomes in the universal set, which is 36. So you get 1 divided by 6. Let's have a look at the event C, which is that the sum of the dice is more than 7. So it would contain elements like 2, 6, because if you add 2 and 6, you get 8, and 8 is strictly greater than 7. And event C is defined as that when you add the outcome you get from the first die and the second die, the sum of those two values should be strictly greater than 7. Okay, so the possible outcomes could be 2, 6, 3, 5, 3, 6, 4, 4, 4, 5, 4, 6. Again, whenever you are writing the outcomes, you go back to universal set, the sample space, and you see, okay, so now this is my sample space, and you look at each and every other outcome, and you see that, okay, when you add the values, it has to be strictly greater than 7. Okay, so now the cardinality of C here is all the outcomes that are in event C, and the possible number of outcomes that are in event C is equals to 15. So how do we find the probability of C? Again, we use the classical formula, and we'll get this is equals to the cardinality of C divided by cardinality of the sample space. So we get it equals to 15 divided by 36. Simplifying it further, you get 5 divided by 12. Okay, now let's check if A and B are disjoint. If A and C are disjoint, if B and C are disjoint or mutually exclusive, what is really happening? So whenever we are looking for mutually exclusive event or disjoint event, what are we trying to see? We are basically trying to check the joint probability of event A and B. What is the joint probability of event A and B? Basically, we are trying to see what is the probability of A intersection B. A intersection B, basically A is defined as the second die is a 1, B is defined as both dies are displaying the same number. So now if we try to find A intersection B, so these are the possible outcomes in the event A, these are the possible outcomes in the event B. Now when you're looking for A intersection B, you are basically looking for all those outcomes that are both in A and B. So it has to be in both the events. So the only outcome which is in the event A and B is 1, comma 1. There is no other outcome which is in both the events A and B. Therefore, A intersection B contains only one outcome, that is 1, comma 1. And therefore, the cardinality of A intersection B is equals to 1. And again, using the classical formula, we get that probability of A intersection B is equals to 1 divided by total number of outcomes in the sample space, which is equals to 36. And we have probability of A intersection B. Now let's check what is probability of A times probability of B. Clearly, since probability of A intersection B is not equals to 0, we get that it is definitely not mutually exclusive. Now let's see if it is independent or not. So to check that, we'll have to find the what is the value of P of A times P of B. So probability of A is 1 divided by 6. Probability of B is 1 divided by 6, and we get 1 divided by 36. And yes, here, probability of A intersection B is equals to probability of A times probability of B. Therefore, we get that A and B are independent because the joint probability of A and B is equals to the multiplication of the individual probability of A and B. Again, it is not mutually exclusive since the joint probability of A and B is not equals to 0. Let's see what is A and C. So if we go back and look at event A and C, if we're trying to find A intersection C, we are basically looking at all the outcomes that are present in both the events A and C. So here now, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1 are the possible outcomes in the event A, and none of these events belongs to event C. Therefore, A intersection C is equals to empty. It does not contain it does not have any outcome. So both the events A and C do not have any outcome in common. And whenever the joint probability of two events is equals to 0, we call them mutually exclusive events. Therefore, here, probability of A intersection C is equals to 0, and thus A and C are mutually exclusive events. Let's try to see what is probability of A times probability of C. So probability of A times probability of C is equals to 1 divided by 6 times 5 divided by 12, which is 5 divided by 72, which is clearly not equals to 0. So here A and C are mutually exclusive because probability of A intersection C is equals to 0. And A and B are not independent since the joint probability of A and C is not equals to probability of A times probability of C. Let's look at B and C. So if you go back and try to check what is B intersection C, basically it contains all the outcomes that are present in the event B and C. So you'll get that B intersection C contains 4, 4, 5, 5, 6, 6. Okay, so now what do we have? We have that cardinality of B intersection C, that is the number of the possible number of outcomes in the event B intersection C is equals to 3. And we get that probability of B intersection C is equals to 1 divided by 12. Now, again, it is not equals to 0. Therefore, B and C are not mutually exclusive. Let's check if they are independent or not. So probability of B times probability of C is equals to 1 divided by 6 because that is the probability of B, and probability of C is 5 divided by 12. So if you multiply it, you get 5 divided by 72. So what do we get? We get that 5 divided by 72 is not equals to 1 divided by 12. So we get that B and C are not mutually exclusive. So probability of B intersection C is not equals to 0. Therefore, B and C are not mutually exclusive. Also, B and C, probability of B intersection C is not equals to probability of B times probability of C. Therefore, we get that B and C are also not independent. Just to summarize whatever we have done so far, I would just say that if you have two events A and B, then A and B can never be disjoint and independent at the same time. Either it will be independent or it will be disjoint. That is, either it will be independent or it will be mutually exclusive. They cannot be mutually exclusive and independent at the same time. But it is possible that both those events are neither mutually exclusive nor even. So we just saw an example in which we considered three events. The experiment was same. The experiment was just rolling two dice, and we saw that A and B are not mutually exclusive but are independent. A and C are mutually exclusive but not independent. B and C are neither mutually exclusive nor independent. I hope the concept of mutually exclusive event and independent events are clear to you all.